Distributed Systems from Scratch. This is episode 12, Gossip Protocols, the season 2 finale. We've spent 7 episodes building protocols: consensus, replication, partitioning, fault tolerance, distributed transactions. Today we add the last piece, a fundamentally different approach to spreading information through a cluster. The idea behind gossip is beautifully simple: spread information like a rumor. No leader broadcasts an announcement. No coordinator distributes updates. Instead, each node periodically tells a few random neighbors what it knows. Those neighbors tell a few of their neighbors, and so on, and so on. Within a few rounds, every node in the cluster knows the information. It's decentralized, it's fault tolerant, and it scales to thousands of nodes with almost no coordination overhead. Why not just broadcast? Have one node send the information to everyone? Because broadcast doesn't scale. One node sending to all n minus one other nodes is a bottleneck. If that node crashes mid broadcast, some nodes get the message and some don't. And the sender needs to know the full membership list, which itself is a distributed systems problem. Gossip avoids all of this. No single node sends more than a few messages per round. If any node crashes, others continue gossiping, and each node only needs to know a handful of peers, not the entire cluster. The original gossip paper was published by Demers and colleagues at Xerox PARC in 1987. It was titled Epidemic Algorithms for Replicated Database Maintenance. The biology metaphor isn't decoration, it's the actual mathematical model. Information spreads through a cluster the same way an infectious disease spreads through a population. A node that has new information is infected. It contacts random peers and infects them. They infect their peers. Exponential spread. The math from epidemiology transfers directly. If each infected node infects k others per round, the information reaches all n nodes in O of log n rounds. Here's the core algorithm. It's remarkably simple. Every t seconds, typically 1 second, each node picks k random peers. K is called the fanout, and it's usually 2 or 3. The node sends its latest state or updates to those k peers. It also receives any state from peers and merges it with its own. Then it waits t seconds and does it again. That's it. No leader, no coordinator, no global membership list. Each node only needs to know a few peers. The randomness ensures that information reaches the intercluster through overlapping chains of communication. Let me show you how fast gossip converges. Round 0, one node has the information, the infected node. It's the star in the diagram. Round 1, it tells two random pairs. Now 3 nodes are infected. Round 2, all 3 infected nodes each tell 2 random pairs. Some of those pairs are already infected, wasted messages, but the remaining ones are newly infected. Now 5 out of 5 nodes have the information. In this tiny example, it took just 2 rounds, but the scaling property holds. The number of rounds to reach all n nodes is O of log n. For 1,000 nodes, that's about 10 rounds, 10 seconds at a 1 second interval. For a million nodes, about 20 rounds. Logarithmic scaling is incredibly powerful. There are 3 styles of gossip dissemination. Push. Infected nodes actively push updates to random peers. This is fast for initial spread. The first infected node immediately starts spreading, but it slows down later because as most nodes become infected, you're mostly pushing to nodes that already have the data. Wasted bandwidth. Pull. Nodes periodically ask random peers, do you have anything new? This is slow at the start. Only one node has the data, so most pools come back empty. But it's very efficient at the end because the remaining uninfected nodes will almost certainly pull from an infected one. Push pull. Both sides exchange their state during each interaction. This combines the fast start of push with the efficient tail of pull. Most production systems use push pull. What information do nodes actually gossip? Membership. Who's in the cluster right now? Who just joined? Who left? Who's suspected dead? Failure detection. When did we last hear from each node? What's its heartbeat status? Metadata. In Cassandra, nodes gossip their token ring positions, which node owns which key ranges. They also gossip schema versions and load metrics. Application state. Some systems gossip key value configuration data, aggregate metrics, or feature flags. Gossip is the substrate on which a self organizing cluster is built. Now let's look at the most important gossip based protocol, SWIM, Scalable, Weekly Consistent Infection Style Membership. Published by Das Gupta and colleagues in 2002, SWIM is the gold standard for membership and failure detection in gossip based systems. Here's how SWIM detects failures. A monitor node M wants to check if a target node T is alive. Step 1. M sends a direct ping to T. If T responds, great, T is alive. Done. But what if T doesn't respond? Maybe T is dead. Or maybe the network link between M and T is congested. A direct ping failure isn't conclusive. Step 2. Indirect probing. M picks a few random pairs, P1 and P2, and asks them to ping T on M's behalf. M sends a ping request for T to P1 and P2. They each try to reach T through their own network paths. Step 3. If neither P1 nor P2 can reach T either, T is declared suspect. If T still can't be reached after a timeout period, T is declared dead and removed from the membership list. The indirect probing is key. It eliminates false positives from local network issues between M and T. If multiple independent paths all fail to reach T, the failure is almost certainly real. Indirect probing is what makes SWIM practical. Without it, every network hiccup between two specific nodes would trigger a false failure detection. The monitor would declare the target dead even though the target is perfectly healthy, just unreachable via one particular path. With indirect probing, you get multiple independent observations. If M, P1, and P2 all can't reach T through different network paths, the probability that T is truly down is very high. And here's the elegance. The failure detection information is piggybacked on regular gossip messages. When M declares T as suspect, that information rides along in M's normal gossip exchanges for free. Within O of log n rounds, every node in the cluster knows T is suspect. No separate broadcast needed. SWIM has a three-state life cycle for each node: alive, suspect, and dead. A node starts as alive. If it fails both a direct ping and indirect probes, it transitions to suspect. The suspicion is gossiped throughout the cluster. If the suspect node can't be reached within a timeout, typically several gossip intervals, it transitions to dead. Dead nodes are removed from the membership list. But here's the clever part: a suspected node can refute the accusation. If T learns via gossip that it's been declared suspect, T increments its incarnation number and gossips an alive message. The higher incarnation number overrides the suspicion. T goes back to alive. This self-defense mechanism prevents false positives from permanently removing healthy nodes. Gossip spreads updates quickly, but it's probabilistic. There's always a small chance a particular update misses a particular node. For critical data like replicated database contents, we need a backup mechanism, anti-entropy. Anti-entropy is a background process where two nodes compare their data and fix any differences. The efficient way to do this is with Merkle trees, hash trees where each leaf is a hash of a data block and each parent is a hash of its children. Without Merkle trees, comparing two replicas means comparing every key value pair. A million keys, a million comparisons. With Merkle trees, you start by comparing the root hashes. If they match, the data is identical. You're done. Zero data transferred. If they differ, recurse into the children. Compare the left subtree hash and the right subtree hash. Whichever differs, recurse further. You drill down only into the branches where differences exist. The result: O of log n comparisons to find the divergent data instead of O of n, massively more efficient. Cassandra, DynamoDB, React, BitTorrent, and even Git all use Merkle trees for exactly this purpose. Let me make this concrete with Cassandra, probably the most well known gossip based system. Every second, each Cassandra node gossips with 1 to 3 random pairs. The gossip payload includes token ownership, which node owns which key ranges on the consistent hashing ring. Schema version to ensure all nodes agree on table definitions. Load information, disk usage, query load, latency statistics. Heartbeat state, a generation number and version counter used for failure detection, and node status, alive, suspect, or dead. Crucially, Cassandra's cluster management is entirely gossip based. No configuration server, no zookeeper. The cluster is self organizing. New nodes join by gossiping with seed nodes, learning the topology, and claiming their position on the ring. Gossip is everywhere in production systems. Consul and Serve from HashiCorp use Swim with Gossip piggybacking for service discovery and health checking. Their open source library member list implements the Swim protocol and is used by dozens of projects. Redis cluster uses custom gossip to propagate slot assignments and handle failover coordination. CockroachDB uses a gossip layer for distributing node liveness information, store capacity data, and system configuration. And Amazon's Dynamo, the internal system behind the famous 2007 paper and the ancestor of Cassandra and React, is one of the foundational descriptions of using gossip together with anti-entropy for membership and replica metadata management. Let me summarize gossip's properties. On the guarantee side, gossip is scalable, O of log and convergence, fault tolerant. Redundant paths mean no single node failure blocks propagation. Decentralized, no single point of failure. Lightweight, low per node overhead. And simple, the core algorithm is a handful of lines. On the limitation side, gossip is eventually consistent. There's always a window where different nodes have different information. It consumes bandwidth that grows with cluster size. Every round, every node sends k messages. There's no ordering guarantee. Messages arrive in whatever order the random selections produce. Convergence takes seconds, not milliseconds, and false positives in failure detection are possible. Suspect doesn't always mean dead. It's important to understand that gossip and consensus are complementary tools, not alternatives. Consensus, Raft, Paxos gives you strong agreement on a single value among a small group of nodes, typically 3 to 7 nodes. It requires quorums. It provides consistency. Gossip gives you eventual dissemination to a large number of nodes, hundreds or thousands. No quorums. Eventually consistent. Many production systems use both. CockroachDB uses Raft for data replication within each range, strong consistency, small group, and gossip for cluster-wide metadata propagation. Eventual consistency, entire cluster. Cassandra uses gossip for membership and token ring management, and leaderless quorum-based replication for data operations. There are different tools for different jobs. Use consensus when you need agreement, use gossip when you need dissemination, and with that, season 2 is complete. Let's look at what we've built. 7 episodes, 7 core protocols. Episode 6 and 7, consensus, Paxos and Raft. How nodes agree on a single value. Episode 8, replication, single leader, multi-leader, leaderless. How data is copied across machines. Episode 9, partitioning, how data is split across machines. Range partitioning, hash partitioning, consistent hashing. Episode 10, fault tolerance, timeouts, circuit breakers, bulkheads, chaos engineering, how systems survive failures. Episode 11, distributed transactions, two-phase commit, sagas, SSI, how operations coordinate across services. And episode 12, today, gossip protocols, how information disseminates through a cluster without central coordination. These 7 protocols are the building blocks. Everything in season 3 is built by combining them. Final takeaways for this episode. 1. Gossip spreads information epidemically, reaching all n nodes in O of log n rounds, 1,000 nodes in about 10 seconds. 2. Swim combines failure detection, direct and indirect pinging, with gossip dissemination. Failures are detected reliably and propagated for free on existing gossip traffic. 3. Anti-entropy uses Merkle trees to efficiently find and repair data differences between replicas. O of log n comparisons instead of O of n. 4. Gossip is eventually consistent. It's not suitable for strong agreement on values. Use consensus protocols for that. 5. Real systems use both gossip and consensus together. Gossip for membership and metadata across the whole cluster. Consensus for data agreement within small replication groups. Season 3. Building real systems. We have the theory from season 1. We have the protocols from season 2. Now we put them together. Episode 13. Distributed storage. How systems like Google File System, Bigtable, and LSM tree-based storage engines work using the protocols we've learned. Episode 14. Stream processing. Kafka, Flink, and the challenge of exactly once processing in a distributed world. Episode 15. System design patterns. The architectural patterns that combine everything. How to design a URL shortener, a chat system, a distributed cache. From protocols to production systems. That's episode 12 and the end of season 2. Gossip protocols. Epidemic algorithms that keep clusters self organizing without any central authority. Season 3 starts next. We're building real systems. Thanks for watching.